So let us understand adjoint of a matrix. So adjoint of a matrix is the transpose of a matrix obtained by replacing each element by its cofactor. So we will understand this definition by considering an example. So find the adjoint of 1 minus 1 2, 2 3 5 minus 2 0 1. So first, to calculate the adjoint, we need to calculate the cofactor of each element. So the cofactor of the first row elements will be a11 equal to 3501. So 3 minus 0, which is equal to 3. Next, a12. So a cofactor is obtained by deleting the first row and the second column. So we get minus into the determinant value 2 plus 10, which is equal to minus 12. A13 will be obtained by deleting the first row, third column. So we get 2 3 minus 2 0, 0 minus of minus 6, which is equal to 6. Next, cofactors of elements of second row, a21. So 2 plus 1 is an odd number, so we get a negative sign into the determinant minus 1 2 0 1, and we get plus 1. A22, again 2 plus 2 is even, so positive sign into the determinant 1 2 minus 2 1, which equals 1 plus 4 equal to 5. A23, 2 plus 3 is odd, so negative sign into determinant 1 minus 1 minus 2 0, which is equal to plus 2. Next, cofactor of element of third row are a31, which is obtained by deleting the third row first column, and 3 plus 1 is a even number, so positive sign into the determinant minus 1 2 3 5, which equals minus 11. Next, a32, 3 plus 2 is odd, so negative sign. So negative sign into the determinant 1 2 2 5, we get minus 1. A33, 3 plus 3 is even, so the determinant 1 minus 1 2 3. So on simplifying, we get 5. So we have calculated the cofactors of all the three rows. So we will replace each element by its cofactor first, and then take the transpose of the matrix. So adjoint of A will be equal to 3 1 minus 11 minus 12 5 minus 1 6 2 5. So while calculating the adjoint, the first step is we need to calculate the cofactors of all the elements. Replace each element by its cofactor, and then take the transpose of the obtained matrix. So next we will consider a result. If A be any given matrix of order n, then A into adjoint of A is equal to adjoint of A into A, which equals determinant of A into I, where I is the identity matrix of order n. So we'll consider an example on the above result. So for the matrix 2 3 minus 4 minus 6, we need to verify A into adjoint of A is equal to adjoint of A into A, which equals determinant of A I n, where n indicates the order of the given matrix. So first we will calculate the cofactors of the given matrix. So first we are calculating the determinant, that is the third part. So minus 12 minus of minus 12, which is equal to minus 12 plus 12 equal to 0. So determinant of A is equal to 0. So 0 into the identity matrix 1 0 0 1, we get a 0 matrix of order 2 cross 2. Next we will calculate the cofactors using the sign notations plus minus minus plus. So a11 it will be minus 6, a12 it is minus 4, into the minus sign we get plus 4. Similarly a21 will be minus 3 and a22 will be 2. So adjoint of A will be equal to minus 6 4 minus 3 2, the transpose of this obtained matrix. So transpose will be equal to minus 6 4 minus 3 2. So we need to multiply the matrix with the adjoint. So adjoint we have obtained matrix A is already given. So using the product of two matrices, we obtained minus 12 plus 12 minus 18 plus 18. Next the multiplication of elements of second row and the first column is 8 minus 8. Next second row into second column we get 12 minus 12. So on simplifying we have 0 0 and 0, which is a 2 cross 2 0 matrix. Similarly A into adjoint of A, 2 3 minus 4 minus 6 minus 6 minus 3 4 2. So on multiplying the two matrices we get the result as a 0 matrix of order 2 cross 2. So from the three equations obtained, we can say A into adjoint of A is equal to adjoint of A into A, which equals determinant of A into identity matrix. Next, verify A into adjoint of A is equal to adjoint of A into A, which equals determinant of A into I for the matrix 1 minus 1 2 3 0 minus 2 1 0 3. So again let us consider the given matrix. So first we will calculate the determinant of A. So we will expand it using the elements of first row. So we get 1 into 0 minus 0 minus of minus 1 into 9 plus 2 plus 2 into 0 minus 0. So on simplifying we get determinant of A as 11. So determinant of A into I, we get 11 into the identity matrix of order 3 cross 3, which equals 11 0 0 0 11 0 0 0 11. So next we will calculate the cofactors of the elements of A. So A11 will be equal to 0. Next A12 will be equal to 9 plus 2 into minus sign, which is equal to minus 11. A13 will be equal to 0. Next A21 will be equal to minus 1 into 3 minus 0, so which is plus 3. A22 equal to 3 minus 2, which is equal to 1. A23 is equal to 0 plus 1 into minus sign, we get minus 1. A31 equals 2 minus 0. A32 is equal to minus 2 minus 6, which is equal to plus 8. Next A33 is equal to 1 into 0 is 0 and 3 into minus 1 is plus 3, which equals 3. So we have calculated the cofactors. Next we will be calculating the adjoint of the matrix. So adjoint of A will be equal to 0 minus 11 0 3 1 minus 1, so 2 8 3. So this is a matrix in which every element is replaced by its cofactor. So we need to take the transpose of this matrix to obtain the required adjoint. So we get 0 minus 11 0 3 1 minus 1 2 8 3 as the adjoint of A. So we will verify the other two parts of the equation. So first A into adjoint of A, matrix A is given, adjoint of A we have obtained. So on multiplying these two matrices, we get a 3 cross 3 matrix which equals 1 0 0 0 11 0 and 0 0 11. Similarly, we will calculate adjoint of A into A, which equals 0 3 2 minus 1 minus 11 1 8 0 minus 1 3 into 1 minus 1 2 3 0 minus 2 and 1 0 3. So on simplifying these two matrices, we get the elements as 11 0 0 0 11 0 0 0 11. So from the three equations we have obtained, we can see we are getting a matrix equal to 11 0 0 0 11 0 0 0 11 in all the three cases. Therefore, A into adjoint of A is equal to adjoint of A into A, which equals determinant of A into identity matrix. Definition: a square matrix A is said to be a singular matrix if determinant of A is equal to 0. Next, a square matrix A is said to be a non-singular if determinant of A is not equal to 0. So if A and B are non-singular matrices of the same order, then A into B and B into A are also non-singular matrices of the same order. So here we have divided the matrices into two types based on the value of the determinant, that is singular matrix and non-singular. So if determinant of A is equal to 0, it is singular, and if determinant of A is not equal to 0, we get a non-singular matrix, and the product of two non-singular matrices is also non-singular. Next, result 2. If A and B are square matrices of same order, then determinant of A is equal to determinant of A into determinant of B. So result 3. If A is a non-singular matrix of order n, then determinant of adjoint of A is equal to determinant of A raised to n minus 1. So we will consider the proof. Consider a matrix of order 3 cross 3. So A into adjoint of A is equal to determinant of A into I, where I is the identity matrix of order 3. So we already know A into adjoint of A is equal to determinant of A into I. So we will substitute the values of I, which is 1 0 0 0 1 0 0 0 1. So on simplifying, we get determinant of A into 0, that is we are multiplying each element of the matrix with determinant of A. On simplifying, we get determinant of A into adjoint of A equals determinant of A 0 0 0 determinant of A 0 0 0 determinant of A. So take determinant A out from each row, we get determinant of A 3 times, which equals 1 0 0 0 1 0 and 0 0 1. So on simplifying, we get determinant of A to the power 3 into 1. Therefore, adjoint of A is equal to determinant of A raised to 2. Note, if A is a non-singular matrix of order 3 cross 3, then adjoint of A will be determinant of A square.